Hello everybody, and welcome to 4.3, Multiplying and Dividing Rational Expressions. Now first of all, just understanding what a rational expression is, just touch up. Rational expression is essentially, like if we look at right here, at this problem that we're going to be doing here in a bit, this here is a rational expression. And the idea behind it is we have some kind of polynomial on top, divided by some kind of polynomial on the bottom. It's rational because it's in the form of a fraction, and this is what we're doing. We're just going to be simplifying these. So we're not solving anything today. We're literally just going to be taking things that don't have equal signs and just kind of reducing them into their smallest forms. All right, so let's go ahead and look at this first one here, where we're going to be writing equal rational expressions. So first we're going to write an expression equal to x plus 3 divided by x plus 9 to find the domain. All right, now it's going to be kind of a weird problem, but it's really just trying to teach us two things. The first thing it's trying to teach us is that we can multiply by 1 all day. Multiply by 1 all day. We'll just put all day. Why not? And the idea is that we can literally keep multiplying as long as the numerator and denominator are the same. We can basically multiply our expression by whatever we want. We just have to make sure that the whatever we're multiplying by equals 1. And then the second thing that they want to establish is that the domain cannot include where x equals 0 in the denominator. All right, and you'll see what I mean by that here in a second, but I mean, it should be clear that when you have 0 in the denominator, the function becomes undefined. And so essentially what we're going to do is we're going to take this expression they give us here, and we're going to multiply by a few things, and then we're just going to define the domain by the things we multiplied by. So let's just go ahead and jump into it. So I can show you what I'm talking about here. All right. So let's just take the original thing they told us here. So x plus 3 over x plus 9. X plus 3 over x plus 9. And let's just go ahead and start multiplying it by some stuff. So let's multiply this by, I'm picking these numbers, by the way, so it really doesn't matter. Let's do x minus 6 over x minus 6. And we're allowed to just multiply this by this because x minus 6 over x minus 6 is just 1, right? Because it's the top and the bottom are the same. And then let's also multiply this by let's just say x over x. Why not? Right? So let's just go ahead and multiply these out. So first I'm going to just multiply the tops. So I have x plus 3 times x minus 6. And that's going to give me, let's see, x squared. I have a plus 3x and a minus 6x, so minus 3x. And then 3 times 6 is 18. So minus 18. And then that's all times x, right? That's our last number here. Because we're just multiplying across, right? So x times 3 times x minus 6 times x. So we did these two first, and now we have this one last. So now we're just going to multiply that by x, and we're going to get x cubed minus 3x squared minus 18x over, well, let's do this one. So we have x plus 9, right, times x minus 6. So it's going to give us x squared. We're going to have a 9x and a minus 6x, so that would be plus 3x. And then we're going to have plus 9 times negative 6, which is negative 54. So this is going to give us, when we multiply by x, we just distribute the x across, right? Because now we're multiplying by this third piece. All right, and now we're going to get x cubed plus 3x squared minus 54x. And really all we did was we took this our original piece here, right? We took this guy right here, and we just picked a couple things to multiply it by. And now what I'm going to show you is how we define the domain. So really all we're going to say is that the domain is that x cannot equal, well, what can it equal? Well, if we look at the denominator, right here, if any one of these pieces equals 0, then the whole denominator would be 0, right? Like, in other words, if x was negative 9 here, then we'd have negative 9 plus 9, which would give us 0, and then 0 times this is 0, and then 0 times this is 0, so the whole thing would be 0. So basically, where each of these pieces would equal 0 is what our domain cannot be. So our domain, x cannot equal negative 9, it also can't equal positive 6, and then for this other x down here, it just can't be a 0, right? So this is what the domain cannot be. So this here is an equal expression to what we had, right? We didn't change anything with this, right? It's the same value, right? But it's just we multiplied it by more stuff, right? It got longer. And this is the domain. It's the domain of x such that x cannot equal these numbers. All right, cool. So like I said, the whole point of that is to teach us two things. One, we can multiply by 1 all day, right? In other words, we can multiply by x minus 6 over x minus 6, and we can multiply by x minus x, or x divided by x, sorry. Those are just 1, right? Because anything over itself is just 1. And then the domain cannot include where x equals 0 in the denominator, which here we have this binomial x plus 9, so x cannot equal negative 9. We have x minus 6, so x cannot equal positive 6. And then we just have x, therefore x cannot equal 0. All right, cool. So let's go ahead and go up here. All right, simplify a rational expression. Now, I just want to clarify what simplify means. And if we think about, like, if we just had a fraction, right, we're just reducing the top and bottom by pulling out as much as we can. So in other words, if I had like 4 over 6, right, if I just had a fraction like this, if I was going to simplify it, I would have to divide the top and bottom both by 2, right, because 2 is the greatest common factor, and that's going to give me 2 over 3. And now we have a simplified fraction, right? Well, it's the same idea for rational expression. We're gonna find out what these have in common. We're gonna remove them. We're gonna remove them from the top and bottom, and then whatever's left over is going to be our simplified form. All right, so I'm glad that this problem here has one of these little things up here, because we have a 4 minus x squared, and we're going to try to factor this. And in order to factor this, if we only have 2 terms here, we know that we're going to have to use difference of squares. We have a 4, which is 2 squared. We have an x squared, which is just x squared, right? But it's in the wrong order. And if we just flip it, it's going to be this, right? It's going to be negative x squared plus 4, right? Over, and then let's go ahead and just factor this bottom piece. What multiplies to make negative 10? That adds to make 3, right? So if we think of this, I'm thinking, let's see, 10 is going to be 5 and 2, right? So if we have positive 5 and negative 2, that would work, right? So we have x plus 5 and then x minus 2, right? Because 5 times negative 2 is negative 10, and then 5 minus 2 essentially is 3, right? Okay, so let's focus more on this top again, right? All we did was just factor the bottom real quick. If we actually take a negative, if we take this term and take a negative 1 out of both sides, it'll get it into the form that we need. So this is kind of the trick to this, right? So if we take a negative 1 out, right, we're going to get negative 1 times this just becomes x squared, right? And then negative 1 times positive 4, it becomes negative 4. And now we have the form that we need so that we can find a difference of squares, right? So it would be this over just the same thing as before, x plus 5 times x minus 2. And now let's go ahead and simplify the top. So this x squared minus 4, hopefully you guys recognize this difference of squares pattern, is going to be x plus 2 times x minus 2. And then the bottom is going to be x plus 5 times x minus 2. Okay, and just like up here, right, just like when we had our problem up here, we took what was common among the top and the bottom, and we divided it out of both. Well, it's going to be the same here, right? This is x plus 2 times x minus 2, and this is x plus 5 times x minus 2. So you'll notice the top and the bottom both have an x minus 2 in common. So we can just divide both of them by that. In other words, they're just going to cancel out, right? Because if we're multiplying both, this is basically just taking one out, right? So now, this will simplify into x plus 2 over, I forgot to bring the negative 1, right? So this is negative 1 times x plus 2 over x plus 5. And this is it, right? We can't really take anything else. So this would be our answer. Negative 1 times the quantity x plus 2 over x plus 5. All right. So really the idea behind these problems is that first we take this, we factor it as much as possible, right? We break it down into this form down here. And then whatever common factors they have, we can remove those common factors. And that's essentially how we're going to simplify one. All right, so what if we're multiplying a couple of these, right? So this was one piece, right? And you'll notice that now we're in multiply rational expressions. We have two pieces. We have this one here, and then we have this one here. So if we have two pieces, how would we do that? Well, let's think about what would happen if we had a fraction, right? Because that's essentially what we have. If I have, let me make something up here. If I have 2 over 4 times, let's just say like 3 over 8. It doesn't really matter, right? Well, what we can do is we can take, well, first of all, we're just going to multiply across, right? But before we multiply across, the thing that we do is we try to get rid of every factor that we can, right? So in other words, this 2/4, I can take a 2 out of the top here, right? And this will turn into a 1. And then just for the sake of it, I know that I could take it out of this 4. I'm going to show you, right, that we can take it out of anything. Because this is going to be, right, this is going to multiply across, so it doesn't really matter which one we take it out of. And then, of course, we'd get 3 over 16. But the point is anything on the top and anything on the bottom, if they're shared, they can be removed. So let's take that back to this problem here, right? If I just kind of multiply everything across, right, I have a 2, I'm going to do the numbers first and just kind of combine them, and then a 3, and then an x, and then an x squared, so that's like, what, 2 more x's? And then a y. And that's kind of everything on top, right? And then everything on bottom is just the number first, so 4, y, z, z, right? And it's kind of like when we found the GCF, because that's essentially what we're doing. So we're going to remove all the pieces we have in common. Now, one thing you should kind of see is that a 2 and a 4, right? That we can eliminate the 2, and this one will turn into a 2, right? All right, and then the 3 won't match with anything. We have a bunch of x's. It looks like we also have a y in common, so let's strike these y's. And all we have left is 3x cubed over 2z squared. All right, now, there's one more thing we have to do, right? Because we have a rational expression. So we need to make sure that we're clear, right? If we are looking at this problem, right? If we look up here, what's in the original rational expression? Well, we have z's in the denominator and we have y's in the denominator. So we need to be clear that for our domain, it's important to do this every time, y cannot equal 0 and z cannot equal 0. Both of those are true, right? We can't have it either way. All right. Cool. So let's go ahead and try one here. This one's a little bit longer, but no problem, we can do it. So you'll notice that in this one, we don't just have factors like before, right? Up here, we just had a bunch of things multiplied together times a bunch of things multiplied together. Here we have trinomial and a binomial. So we have things that are being added. So we have to factor those before we can actually start the problem. Then we can kind of condense everything that we have. All right, so let's get into this. So we have 5x over x plus 3 times x squared plus 6, or x squared plus x minus 6 over x squared plus 2x plus 1 times x squared plus x over 5x plus 10, or minus 10. So let's go ahead and do some math. So first of all, let's factor everything. So I'm going to do 5x over x plus 3 times, let's factor this, x squared plus x minus 6. Negative 6 can be a positive 3 and a negative 2, right? Positive 3, negative 2 would give us the plus 1 we need. So this is going to become x plus 3, x minus 2. And then on the bottom, we have x squared plus 2x plus 1. 1 times 1 equals 1, and then 1 plus 1 equals 2. So this is just x plus 1 times x plus 1. And then times, well, here on this one, we don't really, there's only two terms. We don't have a difference of squares because there's no subtraction. We're just going to take an x out of both. That's all we can really do. So we'll have an x, and that'll leave us with an x plus 1. And then over 5x minus 10, looks like we can take out a 5 from both. So let's do that. And we're going to get x minus 2. All right, now, if we look at this just like before, right, the reason why we did this up here in the first place is you'll notice that any factors that are up top, right, all these little pieces that are being multiplied together, anything that's being multiplied up top can be eliminated by anything that's being multiplied on the bottom. So even though it looks like we have like a 5x, like even though it looks like this is one piece, this is one piece, and this is one piece, everything up top, the 5x, well, this is actually a 5, an x plus 3, an x plus minus 2, an x, and an x plus 1, right? And then on the bottom, we have an x plus 3, right? This is all, anything that's added is just one piece, right? So an x plus 3, x plus 1, x plus 1, a 5, and then an x minus 2. So what we're going to do is we are going to eliminate everything that we can eliminate. So, okay, I have an x plus 3 here, and an x plus 3 here. Cool. I have a 5 here, and a 5 here. X plus 1, x plus 1, x minus 2, x minus 2, and what do we have left? Well, it looks like we have an x times an x, which is just going to leave us with x squared, over x plus 1. Is there anything else? No, just x plus 1. And that's, of course, where x cannot equal, well, let's just look at the denominator, right? We have an x plus 3, so x can't equal negative 3. X plus 1, so x can't equal negative 1. And we have an x minus 2, so x cannot equal 2. So x can't equal any of these things, so this is your answer, right? And remember, you always have to establish the domain. So we've multiplied everything across, we've cut out all the factors that they have in common, and we've established the domain. So this is our answer. All right, so that was multiplying. Now let's divide. And really dividing is the same thing as multiplying, we just have to add one step. And it's the step that makes me hungry every single time. You probably recognize this. We have keep. We have flip. And then we have change. And of course, this is referring to like the sign. In other words, it's going to become multiplication, right? So just like in fractions, right? If we have like, I'm just going to make this up, 4 over 3 divided by like 2 over 1, right? What this is going to become is 4 over 3 times 1/2, right? We keep the original fraction, we flip the second fraction, and then we change the sign. And then, of course, we just multiply across just like we did before. So we can cancel factors. This is going to become a 2. This will become a 1. So we have 2 over 3, right? This would be our answer. Well, guess what? We're going to do the exact same thing, but we're going to factor stuff first. It's really the only difference. All right, so let's just go ahead and do our keep, flip, change first. So I have x cubed plus 3x squared plus 3x plus 1. over 1 minus x squared. And then, of course, it's divided by this, right? So what we're going to do is we're going to change the sign to multiply, and then we're going to flip it. So this is instead going to be x squared plus 3x minus 4 over x squared plus 5x plus 4. All right, cool. So far, so good. Now let's factor. Oh, didn't mean to do that. Make this a little bit longer. Cool. Okay, so let's go ahead and factor this stuff. First of all, we have x cubed plus 3x squared plus 3x plus 1. Now, you'll notice that if I put this 1 here, right, we have a 1, 3, 3, 1. Hopefully you remember from Pascal's triangle that this is what is known as, this would be the third step, right? And this is what is known as the sum of cubes. If you don't remember that, that's fine, right? But that's how you're going to factor this. We know that because we have this, we have a 1 in the front and in the back, and that these are 3's, that this is actually the same thing as x plus 1 cubed, right? Which is x plus 1 times x plus 1 times x plus 1. And like I said, this is just a pattern that I recognize. If you don't recognize this pattern, you just have to look it up, right? There's no other way to do it. But hopefully you recognize the 1, 3, 3, 1 pattern. All right, and then on the bottom, we have 1 minus x squared. So let's use the trick we had before, right? This would be 1, or if we changed it, right, it would be negative x squared plus 1, right? And just like in this problem over here, right, the first one we did, we, where are we? Yeah, here, right? We had the negative x squared plus 4, and we multiplied it by negative 1 so that it flipped, right? And then it became this. So that's what we're going to do over here. So I'm actually just going to, for the sake of the video, just erase this, right, and write it in the proper form. So we're going to take a negative 1 out of each of these, right? So if we take a negative 1 out, it's going to become x squared minus 1, right? So that's what I'm going to do. I'm just going to rewrite that here. The magic of computers. Voila. Okay. And then let's do this. So we have x squared plus 3x minus 4. I see a plus 3x and I see a 4. Anytime the numbers are right next to each other, you know it's going to be the number and 1, right? So we have negative 4. I'm seeing multiply that by positive 4 and negative 1. Positive 4 and negative 1 will equal negative 4 when they're multiplied. And then positive 4 and negative 1 will give us 3. So we're going to multiply by x plus 4x minus 1. Right? And I just factored this piece up here. And then the bottom, we have x squared plus 5x plus 4. That's just going to be 4 and positive 4, positive 1, right? Because positive 4, positive 1 will multiply to get 4, and 4 and 1 will add to get 5. So this is going to be x plus 4, x plus 1. And if the thing that's getting you held up is just me factoring these pieces, really we just need to practice factoring trinomials, right? I understand, like this first one here is a pattern that's kind of rare, right? So I understand if you don't recognize that one right away, right? But, I mean, these trinomials we should be able to factor pretty easily. If you're getting stumped with those, just come see me. There's a ton of practice problems you can do to get faster at those. All right, so the last one we're going to talk about here is this one in the bottom left, right? So we have negative 1 times x squared minus 1. So the negative 1 we're going to keep out here, but x squared minus 1 is a difference of squares because we have an x squared minus a 1 squared, right? Because 1 squared is just 1. So this is going to be rewritten as x plus 1 times x minus 1. All right, and now let's go ahead and pull out everything we can, right? So down here, I have, an x plus 1 here and an x plus 1 here. It looks like an x minus 1 here and an x minus 1 here. And then here's another x plus 1. Let's get rid of those. And then the x plus 4s. Okay, so we took out everything from the bottom, right? So there's really not a lot that's really left at this point. So we just have What's left up here? X plus 1. So our answer is just x plus 1 over negative 1, essentially, right? Which is the same thing as what? Negative x plus 1, right? And then we can even distribute that, so it's like negative x minus 1, I guess. It doesn't really matter. Like, these are all the same thing, right? And that's where x cannot equal. Well, what can't it equal? Well, let's go back up to here when we factored, right? We have an x plus 1, so it can't equal minus 1. So it can't equal minus 1. We have an x minus 1, so it can't equal plus 1. And then we have a plus 4, so it can't equal minus 4 either. All right. And that's it. That's our answer, right? We can just put a box around this. You could have left it in any of these like answers that we got here towards the end, and that would have been fine. But yeah, just because they're all equally simplified, because all the factors are removed. That's all that really matters. All right, real world application, and then we're done. So last one here. All right, a company is comparing the efficiency of two package prototypes. The efficiency is calculated using the ratio of the shape's surface area divided by the volume. And then they give us the shapes here. So shape A looks like it has a length, width, and height, each of 2x. And then it looks like our B here is a cylinder with radius x and height 2x. So we can find the surface area and volume. Here they give them to us, but we could have found them, right? Surface area is just, if we were to cover this in wrapping paper, what would we need, right? Well, each of these squares is going to be 2x times 2x, right? So in other words, each square is 2x squared, which is like this little piece right here, right? 2x squared. And then there's going to be 6 of them because there's 6 sides to a cube. So that's how they got the 6 times 2x squared. And then the volume is just length times width times height, which is just 2x cubed, which makes sense. And then I don't know if you remember the surface area of a cylinder, but it's actually kind of neat, right? First of all, the top and the bottoms are just circles. So we just have the area of the top and the bottom, and the area is pi r squared. So in this case, pi r squared is just pi x squared. So if you look down here, you'll see pi x squared, and then there's 2 circles, right? The top and the bottom. So that's why it's 2 pi x squared. And then the middle part of a cylinder is actually really cool. It's actually just a rectangle with the width of the circumference of the circle. So like this here, if we had a rectangle, the circumference of the circle is actually this, like the width here. And the circumference in this case would be what? It would be, it's 2 pi r. So in this case, it's just 2 pi x, right? And that's what, if you look, you see 2 pi x is here. And then it's that times the height, right? Which in this case is 2x. So that's why this part here is this is actually for the middle piece here. And then the volume is just, it's the area of the circle times the height. So it's just pi x squared and then times 2x. So that makes sense. All right. That was just more of a geometry geek out moment. It wasn't really as important for the problem. But what we're going to do is we're trying to find the efficiency, right? So we need to do the surface area divided by the volume. And we want to know which one of these is going to have a larger ratio, right? That's kind of the idea. All right, so let's just start with A. Let's start with our cube shape, right? So we have 6 times 2x squared. First thing I'm going to do is I'm just going to take this squared and distribute it. So I'm going to have 6 times 2 squared is 4, x squared is x squared, which is of course going to equal 6 times 4 is 24. So we'll have 24 x squared. All right, and then of course we have to divide that by the volume. So let's go ahead and do that now. So volume is just 2x cubed, which is just, I'm just going to rewrite this as 2x cubed, which means of course we're just going to cube the top and the bottom. 2 cubed is 8, and then x cubed is x cubed. All right, and now we have a expression here which we can simplify. So 2x squared over here is going to be 24 divided by 8 is 3. So we're going to have a 3 up top. And then, well, if we have x squared on top and x cubed on the bottom, that's going to be x times x over x times x times x. We can scratch out 2 x's from each, and we're just going to have an x on the bottom. So this is just going to be 3 over x. And we have a lot of extra space here. I'm just going to erase that. Okay. So 3 over x. That's our ratio for our, this is the surface area divided by the volume. So now let's see what we get for b. Well, let's just do it beside it. Why not? Let's do it over here. Let's use our width. Okay, so this is a little bit more convoluted, but really there's not that much math, so it's not too bad, right? We're going to have 2 pi x squared, and then plus, well, it looks like we have 2 pi x times 2x. So if we just have these two things multiplied together, this 2 is going to multiply by this 2, right? So that's going to give us a 4. And then our pi is going to stay there. And then we have an x times an x. So that's going to give us x squared. And this is actually kind of neat, right? And we're going to, let's just do this over, let's go ahead and multiply the bottom too. So we have 2 times pi. There's no common there. And then we have an x times an x squared, which is going to give us an x cubed, right? So that's just us like simplifying the top and the bottom here. But now let's simplify a little more. And this is actually kind of neat, right? Because it looks like what are we even going to do here? But if you look at it closely, right, this is 2 pi x squared plus 4 pi x squared. So if I have 2 of these and I add 4 of these to it, right, this might as well say 2 red wagons plus 4 red wagons, right? Like these are the same exact thing. Pi x squared, pi x squared. So this is actually just 6 pi x squared over 2 pi x cubed. All right, same thing as before. Let's just eliminate what we can from top and bottom. I have a 6 and a 2, so that's going to give me a 3 up top. And then the pi's will cancel, right? Pi's cancel out. The 6's, this became a 3, right? And then we have x squared over x cubed, which is actually just going to leave us with an x at the end on the bottom, right? So which one's more efficient? Well, turns out neither of them, right? They're actually equally efficient. They have the same ratio of the numerator and denominator, and that was a really cool problem. I got to geek out over some geometry, and we got to combine some really cool looking like terms. So, all right, well that's it. So let's just go ahead and do a recap real quick. Oh no, what did I do? Okay, let's go ahead and do a recap real quick. All right, so 4-3 multiplying and dividing rational expressions. First, we started off by going over the idea that we can multiply our expressions by any number of expressions as long as those expressions equal 1. We can continue to just add numbers for no reason if we really want to, right? It's just a skill that we have in our repertoire. We never really had to use it this time, but we will have to later. So we had an original x plus 3 over x plus 9. For no reason, we multiplied by x minus 6 over the top and the bottom, and then by x. Again, we're just multiplying by 1 2 different times, but in different ways. And then, of course, we always have to write the domain that we cannot include in our denominator. All right. And then we simplified a rational expression. Simplifying is important because, we used it for the rest of the lesson, right? So we had 4 minus x squared over x squared plus 3x minus 10. First, what we did is we factored, and then we pulled out common factors, and that gave us our final answer here. And what did we not do in this problem? Oh, shoot. That is not good. We did not state our domain. X cannot equal -5 or 2. Okay. See, so we got that one wrong technically, right? All right. Multiple rational expressions. Multiply rational expressions. So if we have 2 rational expressions here, we have 2xy over z, and then we have multiplied by 3x squared over 4yz. I kind of explained that when we multiply rational expressions, it's just like when we multiply fractions. We can take out anything they have in common, right? And then, of course, we still have to establish the domain. So when we come down here, right, we had a problem where we had 3 expressions being multiplied together. All we did was factor the expressions, right? We factored all of these out, and then any factors they had in common on the numerator and denominator, we eliminated, and then we got our result here, x squared over x plus 1, and of course we established our domain. Right, dividing rational expressions. We learned that we can use KFC just like we did with fractions, right?
we use KFC. So if we have this expression divided by this expression, we can actually just look at it as this expression times the reciprocal of this expression, right? We can flip this over, and then we just treat it like a multiplication problem. So see the previous example: factor, eliminate common factors, establish domain, good to go. And then we had this really cool geometry problem where we established a efficiency by determining the ratio of the surface area over volume. And the way we did that was by, of course, writing out the volume or the equation, if you want to call it that, for the surface area and the volume for both shapes A and B. And then all we really did is we multiplied, or we simplified those expressions, right? So we took this expression as a ratio, we simplified it. We took this expression as a ratio, simplified it. Both of the ratios are the same, therefore they are equally efficient. And that is that. 4-3, multiplying and dividing rational expressions. Have a good day.